It may seem that in my previous lectures I'm downplaying the role of transportation in the food production sector, but transportation is a major contributor to greenhouse gas emissions in the U.S., and food production has a lot to do with transportation. According to the most recent U.S. greenhouse gas inventory in 2014, transportation represents about 26% of total U.S. greenhouse gas emissions. And in 2016, the Secretary of the Department of Energy announced that transportation surpassed power generation in carbon emissions for the first time in more than 30 years. Freight transportation currently accounts for less than 10% of all U.S. greenhouse gas emissions, but freight movement is growing with no end in sight, thanks to increasing consumer demand and complexity and length of the supply chain. The Department of Transportation predicts that U.S. freight traffic will increase about 40 to 45% over 2015 levels by 2040. So there's a lot of growth expected in the future regarding freight, but what do we mean by freight? Let's look at the different modes. There are 4 modes of transportation that are used to use freight cargo around the United States and the world. They include air, road, rail, and water. And each of these modes have their strengths. For example, air is all about speed. Trucks carry the vast majority of freight over 3/4, shorter distances under 250 miles. And rail is about distance. About 40% of U.S. freight by ton mile is moved by rail over a distance of 500 miles. And ships carry over 75% of U.S. international cargo, and it's primarily bulk items. To provide some insight into the scale and nature of the transportation modes, I've included several maps. This map is for air traffic, and it just so happens that when it comes to food, the air traffic is dominated by transportation of fruits and vegetables between Central and South America and the U.S. This map shows the density of the global road network in kilometers of route per 100 square kilometers of land area. What's interesting to me is that even though the U.S. looks less dense than Europe, it actually has much more freight transport by road in terms of volume and distance. It is also expected that the number and extent of roads will expand dramatically this century. Globally, at least 25 million kilometers of new roads are anticipated by 2050, a 60% increase in the total length of roads over that in 2010. And about 9/10 of all road construction is expected to occur in developing nations. This map shows the annual tonnage of agricultural commodity flows to total highway flows. So what we see is a lot of strong routes that go from east to west, west to east, and not a lot of north and south routes until you get into the Midwest and, of course, on the east and west coasts. There are about 164,000 miles of highways in the U.S., and of these, 47,000 miles are interstate highways. And 65% of these highways are in rural areas and 35% are in urban areas. And this map shows global rail density, with lots of density in Europe and especially in Germany, and also in Japan and Korea. And this map of the U.S. shows the annual tonnage of agricultural commodity flows to the total rail flows. Here we see freight going from the Salinas Valley area up into the northeast, as well as a lot of produce and grain actually from the middle of the country heading south to Houston and also out to the east as well. Of course, Houston has a major port for international shipment of grains. And here's another colorful map that depicts the maritime shipping routes. We can see the Panama Canal, we can see the Suez Canal here, and also the Strait of Malacca. These are all sort of bottlenecks for maritime shipping. You may ask yourself, how does all this transportation relate to energy use? And this brings us to one of my favorite of all time charts. It's the estimated U.S. energy consumption in 2015, and where we see that there are 97.5 quads of energy usage. You can study this chart at your leisure, but I want to point out a couple things. At the very bottom, we can see petroleum, where there's 35.4 quads of energy that are used. And if you follow this green bar over to the right-hand side, you'll notice that it breaks into two areas. One is transportation, and the other is petroleum for industrial use. So the majority of petroleum is really going towards transportation, and then it moves on beyond that to two areas. One is called energy services, and the other is energy or rejected energy. And what we can see is that a large portion of the energy from transportation is actually rejected. It's being released in terms of friction and heat. It's not actually transporting anyone anywhere. But we have a smaller amount of transportation energy that's going directly to moving people and things around. You'll also notice that there are several other energy sources that support transportation. Up at the top of the page, we have electricity generation, which follows down like this. And that's for electric vehicles. There's also natural gas, and that's for CNG. And then there's even biomass, which comes down like this. And that's for the additives to gasoline mainly. So when we look at this chart for U.S. transportation energy sources, we can see that the vast majority of energy for transportation is coming from petroleum, diesel, which is also petroleum, and jet fuel, another petroleum product. And the natural gas, biofuels, and other inputs are a much smaller percentage. And so, as shown in this chart of the history of energy consumption in the United States, there's a powerful correlation between petroleum consumption and transportation. Here we see that in the 30s, and really after the post-war area in the 40s and 50s, there's an explosion in transportation. In the 1970s, we have the energy crisis, and then more transportation, petroleum consumption up until 2008, when we have another financial crisis. So what's interesting to me is that really since the 70s, there's been a flattening out of transportation petroleum usage. Of course, the challenge for the U.S. is to reduce this petroleum consumption even further. In contrast, when we look at the world energy consumption projections and usage from 1990 to 2040, there is no slowing down, but a gradual increase in energy consumption in all areas. And particularly in liquid fuels, we can see an upward trend. It's expected that this growth will not be taking place in developed countries, and that over half of this growth will take place in Asia, including China and India. And when we ask ourselves, where's all this energy consumption coming from and the related greenhouse gas emissions, we may point towards air travel. As this chart shows, airplanes are 105 times more potent in terms of greenhouse gas emissions than sea transport. But when we look at the overall greenhouse gas emissions by the U.S. transportation sectors, we can see that aircrafts are actually only responsible for about 8% of the emissions, while light-duty vehicles and medium and heavy-duty trucks account for 84% of emissions. Meanwhile, rail and ships and boats come in at 2% for their emissions. As I mentioned earlier, 75% of freight is handled by road transport, and so there's just a lot of trucks out there, and that's why these greenhouse gas emission numbers are so high. Looking at CO2 equivalent emissions at a more granular level, we can see that the pattern holds. This chart shows U.S. freight carbon dioxide equivalent emissions for the top 7 industries by transportation mode, and we can see that the for hire trucks and for private trucks really dominate the freight transport and also the emissions for these sectors. Focusing just on food manufacturing, which is listed as the third most impactful industry, we can see that for hire trucks and private trucks likewise dominate all the other sectors in terms of their carbon dioxide equivalent emissions. After these big picture discussions about transportation, fuel usage, and greenhouse gas emissions, I thought we'd focus on the pragmatic practice of calculating greenhouse gas emissions. There are just three different factors: the distance that the shipment is traveling, the weight of the shipment, and the mode-specific emission factor. While the weight and the distance are pretty straightforward, the emission factors come in several varieties. In this case, here we have modes of transportation in pounds of CO2 equivalent per ton mile. And here's another example of emission factor. This is done more with a metric system. And as you can see, the different emission factors are really broken up into more discrete categories. So there's multiple categories for air, road, and water transportation. So there's really no magic to calculating CO2 emissions for freight. And here's an example of a 20-ton truck traveling 1,000 miles. Step one is you find out your ton miles, which you get by multiplying 1,000 miles by the 20 tons. Step two, you get your weight-based truck emission factors. And then you multiply the ton miles and the emission factors together, and that's how you get your total amount of CO2 units, in this case over 3 million grams of CO2. And then you convert that into whatever final metric that you'd like to use, and the final outcome is 3.24 metric tons of CO2 for a 20-ton truck traveling 1,000 miles. So here are some final food transportation takeaways for you. First, transportation accounts for 26% of U.S. greenhouse gas emissions. That number is going to be increasing, and we also know that that number will be increasing globally as well. There are four modes of freight transportation, and they all rely heavily on petroleum. Water and rail are the most energy efficient. Air is the most inefficient. But road freight is by far the most popular of the transportation modes. And food manufacturing is the third largest industry in terms of freight CO2 equivalent emissions. The vast majority of freight CO2 emissions comes from hired and private trucks. And you should know that distance times weight times emission factor equals the units of CO2 emissions.